Hello and welcome. Today we are going to be talking about combinations and other counting methods. Now we've already learned about permutation, and a combination is like a permutation, right? Except it's whenever items are not used more than once, in the same way that a permutation is, so that that number will change each time. But unlike a permutation, the order of the arrangements does not matter. Okay, let's kind of remind ourselves about what a permutation is and how the order matters in a permutation. Then we can compare that with combinations. So let's consider our three friends, Tori, Megan, and Zen, for the following two scenarios. If they're finishing a 5K run, how many ways can they place in first, second, and third place? Well, again, we're talking about a place, or I guess first and second place. So in a permutation, order matters because first and second place, it could be that, let's see, maybe it goes Tori and then Megan. It could go Tori and then Zen. Those are the two ways that Tori could come in first. It could be Megan and then Tori, first and second place, or it could be Megan and then Zen. Or maybe Zen comes in first place. And so in that case, it could be Zen and then Tori, or Zen then Megan. So you can see that there are a total of 6 possible ways for this to happen. When we talk about this in terms of a permutation, we could say 3p2, or we could say that, you know what, there's for first place, there's 3 possible choices, and then for second place, there's 2 possibilities. All in all, there are 6 different ways that these 3 people could place in first and second place in a race. Now, that's because order matters. When you are running a race, when you're standing in a line, when you're arranging something on a wall, the order matters. But if 2 other friends are chosen to help set up for a birthday party, how many ways could they be chosen? Well, in this case, it doesn't really matter if they're chosen first or not. Like, for example, when Tori and then Megan are chosen to set up for this birthday party, that would be the same thing as if it was Megan and then Tori. There's no need to write both of these. It's still only one group, the group of Megan and Tori. We also could have the group of Tori and Zen, or we could have the group of Megan and then Zen. So you can see there's only actually 3 ways for them to be a group of 2 people. And this right here is actually what makes up a combination. So a combination instead of a permutation is when the order doesn't matter. It doesn't matter if Tori was chosen first and then Megan, or if Megan was chosen first and then Tori. The fact is that this is a group of people that are going to set up for the birthday party. And this is a different group, and this would be a third possible group. So let's go through and get some practice, because one of the more challenging things for students to do is to identify whether something is a combination or permutation. Okay. So students who are successful with this identify that first. 8 students are preparing for a class presentation and need to assign 3 roles: speaker, slide operator, and note taker. How many different role assignments are possible? So what I think of here is these are positions, right? We have the position of speaker. We have the position of slide operator, and we also have the position of note taker. And if someone was assigned to be a speaker, that would be very different than if that person was assigned to be a note taker. In other words, with these positions, the order matters, right? And I mean, it doesn't matter if I write note taker first. I'm just saying that there are positions involved with this. When order matters, that's when we're going to be getting a permutation because order matters. If we were doing that, this would just actually be 8p3, or you could say there's 8 students to be a speaker, there's 7 different students that could operate slides, there's 6 different students that could be note takers. Okay, so we can write it like that. We could say 8p3, or we could grab our calculator and we can do 8 times 7 times 6 to get 336. Let's look at the next one now. 8 volunteers show up to help at a local food bank. A group of 3 is chosen to unload the deliveries. How many different groups of the volunteers can be selected? Well, one of the key words here is this word group. When you see the word group, that means this is going to be a combination. A combination means the order doesn't matter. Now, we haven't quite figured out exactly how to solve this yet, but what we do know is there's going to be less than 336. In fact, we could think of this as, well, there's 336 possible ways that we can choose 3 in a specific order, and if we then ended up dividing out all of those repeated groups, that's what we get. We'll explore that formula in a little bit, but for now, just know that's a combination. A taco truck lets you choose 3 different fillings from a list of 20 possible ingredients. How many different combinations of tacos could be selected? Well, other than the fact that the word combination is in this, there's another way that we can realize that this will in fact be a combination. And that is, does order matter? Well, I'm going to write that here. So when you're making this taco, does it really matter if you put the cheese on and then the salsa and then the lettuce? Or maybe, you put on the lettuce first and then the cheese and then the salsa. Isn't that really the same taco? Like I know there's going to be some diehard people out there that are like, "Oh, no, no, no. The cheese has to go on first so that it can melt with the meat." I get that. But in general, when you take a bite, it doesn't really matter which topping was on first. And that's because we're talking about a group or a handful of things. We just throw them on. The order doesn't matter. Does order matter? No. Because it doesn't matter, that's a combination. Let's go to the next one. During a high school cross-country meet with 50 runners, how many different ways can the top 3 runners finish? Well, when we think about a race, we have to ask ourselves, does order matter? Well, when you're running a race, yes. Yes, order matters. And so what we could do, because order matters, I could write it like this. I could either say 50p3, right? And that's going to be the same thing as just 50 times 49 times 48. And then if you wanted to, you could grab a calculator to see how many ways we could have the top 3 finishers for this. So permutations seem to be very easy. We've already know the p notation, 50p3, and it really just means 50 times 49 times 48. Permutations, order matters. Combination, no, order doesn't matter. You're just looking for a group. So with our combinations, we're going to start out basically with a permutation and then divide out the repeated groups, right? In a combination, all of the included elements doesn't matter. Just like how the order of identical elements does not matter in a permutation. We account for this by treating every element that we select in the combination as identical. Therefore, if we select R elements to be in the selection, we're going to divide by an extra R factorial. That's all. The number of combinations of R items taken from a group of N is given by this formula. NPR over R factorial, which does simplify down to be this. okay? And I do want to kind of point out that this part of our formula, this n factorial over n minus r factorial, that's a permutation, right? That part there is this NPR. It's not super important, but then the reason why we have this r factorial down here is this is just dividing out the repeated groups. That's all. Let's look at some of these again, and we may go back and revisit those problems. 8 volunteers show up to help at the local food bank, and a group of 3 is chosen. This is one of those previous problems. How many different groups of 3 can be selected? Once again, we noticed that it was groups, and that's why we identified the fact that this is in fact a combination. So this will be 8 people to choose from, and we're going to choose a group of 3, 8C3. If we wanted to use our formula, it would actually be 8 factorial over 3 factorial, 5 factorial. Okay? Remember that this part here, that's the permutation. This 3 factorial, these are the repeated groups. So we're just going to divide those out. Now, the other good news is that your calculator can do this for you. Not only can we type it out and say, we could do 8 factorial divided by 3 factorial, 5 factorial, and we're going to get 56. But, so there's 56 groups, 56 different groups of people. That's significantly less than that 336 that we had before, right? That's because we're dividing out all of the repeated ones. Notice down here, though, if you look just above my arrow, there's an NCR button. That NCR button works the same as the NPR. So NCR on Desmos, when you hit it, it says NCR and then parentheses, and then we're going to put 8 comma 3. So just like before, we'll put our first number and then comma, second number. By the way, if you do try to switch those around, and if you accidentally forget and you do NCR and you try to do 3 comma 8, look what happens. Like it says 0. That's because what that really means is if you have 3 people to choose from and you want to make a group of 8, you want to take a group of 8 from 3. How many ways can you do that? 0. That's why this is 0, because there's 0 ways to do that. Next, we have our taco truck. It lets you choose 3 different fillings from a list of 20 possible ingredients. How many different combinations? Okay, so we identified that as one of the key words so that we know that it's a combination. This would just be 20C3. By the way, if I was going to do this without my calculator, it'd be 20 factorial over 3 factorial, 17 factorial. Notice the 3 and the 17 add up to be 20. That's because we have r and n minus r. So you can do it like that in the calculator, but honestly, it's probably going to be easier if we just hit the NCR button. Let's clear this out. And we'll do 20 comma 3. So that's how we would do 20C3 on our calculator, is by writing it as NCR 20 comma 3. Oops, I forgot. So that's 1,140. There's 1,140 possible combinations of tacos that you could get if you're able to choose 3 ingredients. Let's do a few more practice problems. A farmer market stall sells 7 types of fish, fresh bread, and 10 types of jam. You're creating a gift basket that includes 2 breads and 3 jams. How many different ways can the basket be assembled? So remember, when we're doing a basket, this is going to be a combination. Because it doesn't matter if you put in the rye bread first and then the sourdough, or if you put the sourdough bread first and then the rye, it doesn't matter. That's still the same basket. People are just going to be happy and they're going to be like, oh, look, I got these two types of bread. So because of that, we'll say order does not matter. And that's going to be a combination, right? So if order doesn't matter, that's a combination. Let's first look at the bread situation. Our bread situation says that we have uh, 7 types of fresh bread, and what's going to happen is we're going to include 2 of them in the basket. So that means we have 7C2 for the bread. 7 types of bread to choose from, and we're going to choose 2 of them to put in the basket. Next, there are 10 types of jams, and we're going to include 3 of them in the basket. So as far as the jams go, we would say there's 10C3 of the jams. And when we learned about the counting principle, we learned that every time we're going to make a decision, we're multiplying those choices. So we're going to multiply these 2 numbers together. Let's next do 7C2 times 10C3. There we go. You can see on my Desmos calculator that I started out by writing my 7C2 and got 21, and then I did my 10C3 and got 120, and when you multiply those, that's got us our 2520. I also showed you that if you just multiply NCR 7 comma 2, that's like that 7C2, and you multiply that with 10C3, your calculator is going to do that all at once and it will do it just fine. So your calculator can handle that if you just do it all at once. Let's go ahead and look over here to the next one. A local cafe carries 12 tea flavors and 7 coffee blends. You want to stock 3 teas and 2 coffees for a small event. How many different ways can you select these beverages? So we're going to stock them, meaning like we're bringing them to this event. It doesn't really matter the order in which we bring them, and that's why this is going to be a combination, because the order doesn't matter. In other words, we are just taking a group of tea and a group of coffees, and we're just going to bring all of them with us. Okay, so let's make sure we identify the important parts of this. The first thing that I'll note is that we have 12 tea flavors, and we're going to stock 3 of them. So as far as the tea goes, we would say 12C3. And then for the coffees, I see that we have 7 coffee blends, and we're going to bring 2 of them with us. So if we want to bring 2 of them, I would say there's a total of 7, and we want to choose 2 of them. Next, we're just going to multiply those 2 together. That gets us our 4,620 possible ways to stock the tea and the coffee. Again, you can see I chose to do these separately to start out with, which was to say 12C3 got me 220, and then 7C2 got me 21. If I messed up, sorry. Sometimes I read things and my eyes go crossed. I think we're good. There's some really fascinating things about combinations and dealing with some other stuff called the binomial theorem or binomial expansion. There's also Pascal's triangle. There's some really cool things as to how math relates. Now, it is beyond the scope of this lesson, but that's something that you can look up if you're interested in learning more about combinations. Next, let's look at the power of narrowing and expanding some of these choices. The fundamental counting principle shows that the total number of outcomes grows by multiplying the number of options at each decision. And so changing the number of options at each step is going to alter the number of outcomes, even if you just make a teeny tiny little change. Okay, so let's look at a few examples of where this is relevant. A quiz contains 5 multiple choice questions, and if each question has 4 answer choices, how many total answer patterns are possible? Well, when we do a question like this, we've looked at these before. We would say there's 5 questions, 1, 2, 3, 4, 5, and there's 4 answer choices for each one, like A, B, C, D. So this would just be 4 times 4 times 4 times 4 times 4, or 4 to the 5th power, and I believe that's 1024. Just for the sake of it, I'm going to go ahead and check because I would hate to make that silly mistake. But what if you were a good student and you said, you know what, I can rule out some of these. A student can confidently eliminate 2 choices on every question, leaving only 2 choices. How many answer patterns are possible now? Well, we would still have 5 questions, but if we can rule out half of the possibilities, so it'd be 2 times 2 times 2 times 2 times 2, notice that it doesn't rule out half of the possible answer patterns, right? It rules out a lot more than that, right? We went from 1024 possible answer patterns to only 32. Like consider this. If you were taking this quiz and you didn't know any of them and just strictly guessed, well then it's 1 in 1024 chance that you would get them all right. Not very likely. But if you could rule out 2 of them, you read the questions and you say, you know what, I can rule out this one and that one. I can rule out A and B because those answers are just way off. I know they're silly. Well, in that case, you actually have a 1 in 32 chance of being able to get all 5 of them correct. That's pretty good. Let's go on to number 10. You're a Little League coach with 13 players on the team and you need to pick a lineup with 9 players. How many batting orders are formed? Well, this is a situation where we're doing this without replacement. This would be 13P9. And if you'd like that visually, we would just put our 9 blanks because we have 9 players. And we would do 13 times 12, 11, 10, 9, 8, 7, 6, 5. And there's a little over 200 million possibilities. Like, that's a lot. So those of you that think it's easy being a Little League coach, man, you've got 13 players. There's 250 million lineups possible. So cut that Little League coach some slack. If, however, you already know who's going to bat first and you already know who you want to bat third, well, now this actually changes a little bit. So consider this. I'm going to actually draw it out and we'll put our 9 positions. And the thing is, if I know who's going here, like how many choices do I have? I actually only have 1. I know this one, right? This is like for sure Tim is going to do that. So it's not really a choice. It says you know who's batting first. And this is third. It also says that you know who's batting third. Like we're going to put Tommy in for the third place because you know he's really awesome and you want him batting third place. So there's only one choice there. Now when we look at the rest of these blanks that we would have, remember we started with 13 players that we could choose from, but we've already taken away 2. We're locked in with those 2, which means I have 11 choices left. So this is where then I could go through and say, well, I have 11 different kids that I could put in this spot. And then I have 10, and then 9, 8, 7, 6, and 5. Now, if we do this on Desmos and just do 1 times 11 times 1, and so on, there you go. You can see that, yeah, there's still a lot, But man, there's way less than there was. We have 250 times less possibilities this way. Now, I hope that you're looking at this and saying, why did you go through and type all that in? Like 1 times 11 times 10 times 9 times 8 times 7 times 6 times 5. Wait a minute. Isn't that just 11p 7, right? 1, 2, 3, 4, 5, 6, 7. Yeah, because it's going to be 1 times 1 and then times 11p7. Same thing, right? So just a little bit quicker way of doing this. If you kind of know what's going on, and with a little bit of practice, some of these things will start to jump out at you. All right, let's look at a restaurant now. They advertise a customizable bowl with 3 base options. We have 4 protein options and 5 sauce flavors. How many bowls would be possible if sauces were not counted as a part of the combination? Okay, well, that's easy enough. If sauces aren't counted, then what I can do is I'll just get rid of them so I don't even see them. There. Whoops. There. Now, how many bowls would be possible if we didn't count the sauces? Well, that means that we're just going to count just our base options, and we're also going to count the proteins. There's 3 base options and there's 4 proteins. That means there's a total of 12 bowl combinations, or 12 different bowls, right? This is the counting principle. We're not really using permutations or combinations. This is just saying we have different decisions to make, so we multiply the number of choices at each decision. But part B says how many different bowls are possible when sauce flavors are included. Oh, well, there's 5 sauce flavors. So now what we would do is count all of them. We would say we're going to count our 3 bases, we're going to count our 4 proteins, and then we're also going to count the 5 sauces. Remember, because of this counting principle, we just multiply each time, and that will get us 60. So just by including the 5 sauces, we can change the number of possible different bowls from 12 up to 60. Well, right away, this restaurant now kind of seems like it has way more possible bowls. But what if they wanted to go a little bigger and they said, hey, let's add 5 new sauces, right? Hey, let's add a honey mustard, let's add a teriyaki, let's add a Szechuan sauce. Ooh, that sounds good. So if they added 5 new sauce flavors, that means we're going to add those to the original 5 to equal 10. Go. So now what we have is we have our base still, we have our proteins, and we also have our sauces. But now if they added 5 new sauce flavors, it would be 3 times 4 times 10, and now they have 120 possible bowls. Now, think about this for a minute though. Like, from the restaurant's perspective, they can now advertise, hey, look at all the possible combinations that we have. 120 possible bowls. But really, it's just still the same 3 bases. Maybe it's like a white rice, a brown rice, and a noodle. And maybe it's 4 proteins, chicken, beef, turkey, and um, uh, soy. You can tell I don't eat much of it. Tofu, that's what it is. Sorry for my vegetarian and vegan friends out there. So you know, if you only have just like those three bases and the four proteins, like that's cool. But by adding a handful of sauces, you can change from saying we have 12 bowls to we have 120 bowls. I mean, are they really that different? Not really. But what this does do is it allows some businesses to advertise an inflated number of combinations without really changing the number of main ingredients that much. And I don't want to throw anybody under the bus because it's always fun, but like if you think about Sonic and they say we have, you know, like 132,000 possible flavor combinations, yeah, but like if you just have like a handful of sodas and a handful of toppings and a handful of flavors and you just multiply them, yeah, you can get to that really big number pretty quickly. So just be aware that adding one or two additional choices can really change the number of items that you might have or the number of ways that something could go. So I do want to end here with just a brief review of the difference between a permutation and a combination. Permutations, you want to be able to identify them first. Uh, so whenever you see or you identify the fact that something is being arranged, right? If you're hanging something on a wall, if you're lining up, when you're running a race and you're talking about the medals, anything where there is a position, right? Order matters. That's going to be some type of a permutation. A combination occurs whenever you have a group, a team, a committee. Now, we're not talking about positions on the committee, like if there's a president and vice president on you know, serving on this committee for some reason, but like a committee where you just have a group of people. So positionless, so to speak. If you grab a handful of candies from a bucket or something, where the order doesn't matter, that's a combination. Okay, permutations are NCR and combinations are, oh my goodness. Let's change that into a P. There we go. Permutations are NPR and a combination is NCR. In general, the permutations are much, much larger. There's many, many more ways because the order matters. A combination is a group and the order doesn't matter, so there's going to be less of them. All right, good luck as you continue to work through this math. Remember, always try to identify it's a permutation, a combination. And don't forget, some of these are just the counting principle. That's where you could make like a tree diagram, and for each decision, you just multiply the number of choices. Good luck.